Okay, now we're going to learn some truly amazing stuff about these vector derivatives. So we're going to define this special triangle symbol in a way that looks like a regular vector, but isn't quite. So remember that long ago we defined these capital D's as notation for partial derivatives. Now we call this object, or this symbol, del, or in some cases we call it nabla, depending on who you're talking to. So it acts like a vector, but a vector of operators on functions. So we've seen this guy before because if you write del f, okay, f is a scalar function, so if we just put an f over here, right, scalar times a vector, you just distribute that scalar throughout the vector. So it's the vector dx times f, dy times f, and dz times f. And that's the gradient. Okay, so now we've made some sense out of this notation for the gradient, but it goes farther than that. So remember we had two kinds of derivatives of vector fields. We also had two ways to take vector products. So if we look at del dot f, the dot product between the del vector and the f vector, well, that's the x derivative of p plus the y derivative of q plus the z derivative of r, and that is the divergence. And then you might predict, and you'd be right, if we take the curl of f, or I'm sorry, if we take the del cross f, we're going to get the curl. We would write this as the usual determinant between the vector of operators and the components of f. That's how we define that cross product, and if you work it out or look back at the definition, this in fact is the curl of f. So it's pretty amazing that we have two kinds of vector products, two kinds of vector derivatives, and they're so deeply related this way. There's one more important kind of derivative. So you can take the divergence of the gradient. Now remember, curl of gradient is 0 and divergence of curl is 0. But divergence of gradient is not always 0. In fact, it's very interesting. And if you work out what that is, you get this, or in other words, the sum of xxx, fxx, fyy, and fzz. And we have a special notation for this. We can write del squared of f, or sometimes we just write what you would call delta f, but in fact it's not delta. This is called the Laplacian operator. And it plays a huge role, not just in physics, but in all kinds of applications, especially those involving diffusion.